Okie dokie. Is that I'm recording, right? Yeah. Sharing. Okay. So let's go back to our program here. My current hobby each day is to go through my email. I spend a half hour and I unsubscribe. And it seems like each day there's just a new list of emails that I just get from Rand. And there's email addresses that I don't know how it's getting to me. I have like this email that's like Lopez at AOL.com. It's got to be something left over from like the mid 90s where I was maybe doing some questionable hacking activity and was maybe using some extra email addresses, like before they like confirmed email addresses. I'm too lazy for that now. All right. Could I slide that over? All right, good. All right, so looks like, so last time we created a char pointer for a string. All right, so effectively strings are collections of characters, right? And collections in all of our modern languages are stored inside of a contiguous memory. So we talked about it like in terms of arrays, where there's a base address and then we walk with offsets from that base address. So in this case, we have what, 5, 6, so 11. This guy right here is taking up 11 plus 1, 12 total bytes, because we do have this string termination character, this \0, that tells the system to terminate that string. It's kind of like how old style C hacked a char array to behave like a string. Not like a string that's up to our standards. We're used to languages being very string centric today, right? Where we can really just work with strings very conveniently. I'm going to show you a couple examples today where even with the convenience of a character array behaving like a string, we still had to use some extra crap to get it to work. So we're going to see that we don't really like it. We'll appreciate that we'll use the new style strings. I'll show you the new style strings. You're going to see it's pretty similar to Java, and we'll move on with life. All right. But I do think it's an important lesson because it is possible in your career you might run into older style C code. And actually, it's an advantage I've noticed here with online GDB is how easily I can switch my language here. So I actually can show you, like for instance, this code right here. I've given an old style string right here, a char pointer S. And if I run this right now, it should just give me the hello world, right? Oh, actually, number of characters. We wrote a string length thing, searching for the \0 last time. But if I switch this to a newer language and run it again, I'll probably get a warning. Yeah, well, actually, it's an error. C++ forbids converting a string constant to a char pointer. So basically saying, don't use that kind of strings in C++. I might be able to pull it off with an older, that's a pretty old version of C++. Will let me accomplish it there. Yeah, it did. So kind of a cool feature of this online GDB is you're able to pretty quickly kind of test your stuff through different vintages of compilers, because as you see in here, there's a whole bunch of versions of C++. I'm guessing this catch-all one is latest, greatest version of C++. And that guy basically says, look, if you want strings, don't use char pointers, use strings. But anything that says Turbo C on it, this is before we had even graphical user interfaces. This is like back when you were running your stuff on DOS. So that was old enough. Okay. So let me just switch this back to C for the rest of this little example. But hopefully you kind of see that it is kind of up to the compiler as to what it's going to allow and what it's not going to allow, even within the same language. We just saw an example where the most modern version of C++ says, no, you can't do this. And a much, much, much older version of the C++ compiler says, hey, I don't have any problem with it. Go to town. Make sense? Just kind of an interesting concept. So in any case, we're creating a string here. we saw that we proved that the string termination character on our string is a \0 as I've advertised. Why? Because we wrote a function called string length that we can pass the char pointer to, and it will boil down to the number of characters in that string, because I'm counting until I reach a \0. That makes sense? Now, an interesting thing to look at here. So I'll say printf, the string is %s. We'll give it the S there. So this will show us the contents of our string, which is hello world, this guy right here. Now, what I'm going to do is I'm going to actually go ahead and hack our string. So we're going to see that, as I mentioned a few minutes ago, that this whole string termination character is kind of that old school mentality of how can we make character arrays behave sort of kind of like strings so that the programmer has it a little bit easier. Their life is a little bit easier since strings are data types that we commonly might use. So what I'm going to do is I'm going to go ahead and randomly insert a \0 character in the middle of my string. Just going to overwrite one of the characters with it. So I'll go ahead and say S at bucket 4 is equal to a \0. And remember, that's the same thing as saying star S plus 4 is equal to \0 using pointer math. They both are doing the same thing. We'll see plenty of examples of this. But I'll just overwrite bucket 4 with a \0. So this is 0, 1, 2, 3, 4. We probably we'll go bucket 5. That way our output's not just, well, let's go bucket 7. That way our output's not hell. Okay, so I'll overwrite bucket 7. So this is 0, 1, 2, 3, 4, 5, 6, 7. And what this will do is it'll give us hello space W as our string if I go to print it out. So I'll just steal this line. So all I've done is I've added an extra \0 into the middle of that string. So now it'll think our string is actually terminated a little sooner. Did I have to save it? Is it protecting against it? Why is it not letting me change it? Is it because I made that a literal and it's read only? S, that's S. I'm changing S. Inserting a \0 in there. It's not even getting, well, it's not displaying anything on that line. I'm thinking since I made this a literal, it won't let me change the value. Let me force it. 2 is equal to, let's put another W in there. Yeah. All right, so I don't want to spend too much time then on this, but effectively what I would have to do, since I hard coded this to be a string literal, I can't change it. If I want to change it, I have to have access to the memory. So I would have to allocate memory for this guy. So I can include standard lib.h and then use memory allocate malloc, which is the C version of our Java keyword new. The new keyword asks for more memory. Then I would own the memory. Then I would be able to go in and change one of the buckets to a \0, yada, yada, yada. But effectively what would have happened here if I went through those couple of lines is I would have thrown in a \0 here. So when I went to print out the string, it would have printed out that, even though there is a second \0 there at the end that would have been noticed initially. So now what it would be proving is that the way old style C hacks strings is by saying, I will terminate the string at the first string termination character, \0 that I find. So if we were to artificially throw one in, we would get a short-circuited string. Okay. But again, we're not going to be using these old style strings. So let's kind of leave it at that for a second. One last thing I'll do, and this should work since I'm not modifying the string directly, is in Java, if we want to print out a string, we might want to say something like S is equal to S concatenated with LOL, something like that, right? That glues strings together. Well, I'll go ahead and run this, and we're going to see that this plus operator is not defined for string literals. All right, doesn't like this invalid operand to binary plus. Can't use that to concatenate strings. All right, that's a much more modern syntax. Now, you can imagine that back in the early days when we used C, gluing strings together may have been something we wanted to do. Makes sense, right? We might have wanted to do that. So strings couldn't do it to themselves, but there were libraries, string.h. There were libraries that existed that allowed us to do this. And for strings, I think it was strcat, S, and we'll say LOL, and then we'll print out S. What is going on? There. It's changing the memory thing again. I'll just do it directly and we'll move on with life. I'm going to force this to 100 string example. It feels like it's not saving. String cat and string.h takes a character pointer and another character pointer and boils down to a character pointer. Seems reasonable enough. It's in string.h, right? String.h. str cat. Is it printf that doesn't like it? Now it's going to be in a namespace. Let me switch it over to C++. And I will remove standard IO. I'll include that. That should allow us to use. Although now it's going to give us an error saying we can't use string literals. This isn't string.h. Forbids it. So I can't pull it off without allocating the memory. All right, just take my word for it. This guy right here would produce hello LOL or hello world LOL. That guy. A function called string cat that operates on strings. All right. But we would have to own the memory of the string. Unimportant for us since that's not what we're going to be using. But what we should get from this is that old style C strings were not overly convenient to use, although they were more convenient than character arrays. Okay. So from this point forward, let's look at new style strings. So I've switched my language to C++, where we're going to stay for probably the rest of the semester. I'm going to include a library called string that lives inside of the namespace standard. And I'll go ahead and get rid of some of these extra things. I'll go ahead and create a string s is equal to hello world. And then I'll go ahead and display s. So there's my hello world using our new type of string class that exists in the string library in the standard namespace. If I want to print out, if I want to say string s2 is equal to s concatenated with LOL, and then I want to display s2, now we see that this guy behaves like Java strings, right? We can use plus signs to concatenate them together and that kind of stuff. So this more modern string in C++ behaves like the strings that we're mostly used to, because our modern day programming is much more centric around strings. All right, so, and I'm sure we can force it to go back to getting that string cat and stuff like that to work, but it would just take a few minutes to sit there and mess with memory. So I think we probably get the point. All right, so any questions about any of that stuff? All right, so next thing is, let's see, is this the one where I had, here's my C++ class example. So we created a, here's our, just as a reminder, because we want to move back to classes, but I want to explain this arrow thing here. So what I'm going to do is I'm going to go ahead and write it a second time. Actually, I could do it with, these two lines here accomplish the same thing. So when I say P arrow display, it's like the same thing as saying resolve the value that lives at P. then call a function on that value. So this arrow thing is shorthand for resolving a double pointer. The value that lives at P2 is a memory address. When I resolve that memory address, it takes me to an object. To call an object's methods, functions, we say dot display in this case. So I am manually saying I want to resolve the value that lives in P2 to the thing that it points to, which is my instance of person. Then use dot to call one of his members. In this case, it's a method. As opposed to, this is syntactic sugar. This right here says do the identical thing, but doesn't require parentheses and doesn't require the asterisk. It says, look, I understand that what you actually want me to do here is go to the actual person object and then call its method. The arrow gives it that message. Make sense? So it's for a pointer. That's how you call functions on a pointer. And we'll see it a lot because we have the this keyword inside of here. And notice that the this keyword holds a pointer that points to this instance of person. So this guy right here is the same thing as saying this dot fname is equal to fname. These two lines are identical to each other. And they literally mean the same thing. They don't just accomplish the same thing, they mean the same thing. This arrow says to do this first and then call, in this case, this field. All right. So the arrow is made to make our life better, more convenient, less keystrokes, but it's not some sort of magical thing that you ever have to use. It just allows you to avoid writing it like this, resolving a memory address. The punchline for us here should be whenever we see an asterisk during runtime like this, so we're not defining a variable, we're using a variable. An asterisk means the value at that address. That's what an asterisk means. So we say, give us the value at the address that this holds, which is an instance of person, and then call that instance of person's fname field and set it equal to the value that was passed in. All right, make sense? So that's just what that syntax does. For us, we'll just be using that syntax, but understand what it's actually accomplishing under the hood. It's making our life easier by not having to write things like that pretty much all the time, since we're going to be using objects often. Okay. Now, talked about that. Let's look at structs. Did we look at structs already? Okay. So predating classes, and I'll still do this inside of our C++ thing here. I'll go ahead and I'm going to define a variable. I'm going to call this guy a person struct. And we're going to say that a person struct, I'll go ahead. I'm just going to start using our new style strings. All right. So I'm going to say a person struct is going to be a string f name, a string l name, and int age, something like that. These guys are kind of like dictionaries in Python, structs, with one caveat. In Python, Dictionaries are passed by address. So if we pass a dictionary to a function in Python and we make a change to that dictionary, that change is permanent. In C and C++, structs by default are primitive types and they are passed by value. So changes will not be realized. So I'll show you this by an example. All right, so I'm going to write a quick function here, void display person struct. And this guy will take in a person struct P. And we'll do something like cout p.fname. So here's a good example where we are using the dot notation rather than the arrow because P is not a pointer. P is a struct type. Make sense? So I don't have to resolve the value. It is already the value. So since this guy's not a pointer, since it didn't come in as that, P is actually the struct. So that's why I can just say P dot rather than P arrow. So I'll see cout p.fname, put a space, p.lname, put a space, p.age, and then that'll kick it down a line. All right, so this is a function that will display a struct. I think I mentioned it maybe last class that technically, I think we saw that it does work. And it gives us a warning, an implicit definition of a function. Because up here, I'll go ahead and make a call to this guy. Let me build a person struct real quick. So I'll say person struct p1, p1.fname is equal to Mike. p1.lname is equal to Littman. p1.age is equal to 21. And then we'll call display person struct p1. All right, now if I run it this time, I think it gives me a warning, but will run. It'll give me an implicit declaration of display person struct. Oh, this guy is an integer, not a string. Oh, does give me an error. Good. Maybe we saw it was an implicit in one of the other compilers, but that's fine. I think this is more appropriate. It says, look, I have not seen a function here called display person struct. So as we're walking through our code here and we get down to this line here on 28, it's saying, I've never heard of a display person struct. Why? Because we don't define it till later on. So what we would do is we would do what's called prototyping these functions. So up top here, I'll just throw the header of that function up here, prototyping it, kind of saying, look, there will be one of these guys that takes one of these guys as a parameter. I promise you I'll be defining it at some point. But for right now, since I've prototyped it here, you now know that this dude's legit. Oh, sorry. Syntax for this is struct person struct. Syntax for this is struct person struct. My prototype. Person struct. There we go. Whenever you create variables of type struct, you actually have to put in front of it that I am defining a variable of type struct person struct. Good thing for us is we're not going to use structs too much because these are, again, old school. All right, so here's a struct person struct. We filled it up with some stuff. Notice that I'm using a dot notation instead of the arrow notation. Why? Because this guy right here is a actual struct, not a pointer to a struct. So I'm going to write a function down here called change struct, and this guy will take in a struct, person struct, p is the parameter, and we'll go ahead and say p dot f name is equal to Bob, and then we'll call display person struct, passing it p. All right, so this guy's name is change struct, and I'll go ahead and prototype it. So I'll grab that there, put it up here. Now, one thing we've seen already is these prototyping things become something that's not all that commonly used, because modernly we use header files where we effectively have prototyped everything in the header file. Remember when we covered this, the header file and then the C++ file up top, we're including our header file. So what does that do? It effectively pastes the entire contents of this file at the top of it. In effect, we are prototyping stuff. We're just doing it by way of another file. All right, but in this case, we're putting everything in main. So I'm writing a couple of direct functions. So I'll go ahead and prototype them up here. Change struct takes in a struct. I'm going to modify the first name of that guy and then prove that it was modified by calling display person struct. All right, so then we're going to see how what the behavior of structs are when we pass them in as parameters. So I'm going to create my original struct, P1, Mike Littman 21. I'll call display person struct, passing it P1. We saw it printed out Mike Littman 21. Then I'll call change struct, passing it P1. Change struct modifies the first name of the struct, and then calls display person struct again, which should show as Bob Littman 21. Then the question is, when we come back to main and we call display person struct again, P1, is it going to be back to Mike Littman 21, or is it going to still be permanently changed to Bob Littman 21? We see that it reverted back to the original Mike Littman 21. What does that tell us? That structs are passed by value, not by address. When I took in my struct here and I modified the contents of that struct there, it was only modified in the scope of this function. As soon as that function ended, this copy of my person struct disappeared. And when I returned to main, I reverted back to the original version of P1. The original P1 was not actually changed. We changed a copy. So structs are passed just like integers are passed or chars are passed. They're not passed like objects are passed. All right. So that is a difference. If we're trying to compare the languages that we've been exposed to, and we kind of say structs look a lot like dictionaries. It's a collection of name value pairs. That's what a dictionary was. But in Python, when we passed around dictionaries and we made a change, if this was Python, this change would have been permanent. This line would have displayed Bob Littman 21. The behavior would have been different because of how the default way in which dictionaries are passed in Python, which is by address. In C++ and C, the default value, the default way structs are passed is by value. But as C++ developers, we are empowered with a syntax that allows us to say, That might be the default behavior, but that's not the way I want you to work, right? So I can go ahead and have a void change struct by address and have this guy take in a person struct pointer P. And I'll accomplish the same thing in here that I did before with one little caveat. I'll say P arrow first name. Or if you like it better, star P dot F name. Again, they mean the same thing. So what I'm saying here is this guy, P, is a variable that holds an address. How do we know? Because the type is person struct pointer. So the contents of P is a memory address that points to the actual struct in memory. So I'm saying go to the actual struct in memory, change its first name to Bob, and then go ahead and print it out to prove that it worked. Okay, so I'm going to remove, I'll just put it as a comment, this second line here. All right, any questions about how these two things are the same? We're going to be using that arrow quite a bit in here. And I understand that pointers are kind of confusing, but I really want to drive the point home that they're not hard. They're just intimidating because we're not used to directly working with memory. The second we start seeing memory addresses, hexadecimal crap, we freak out, right? As newer computer programmers. This is just nice, friendly syntax that says, you gave me an address, I'm going to go ahead and find the thing that address points to, and then let you get at the thing you want. P arrow F name. I'll often just refer to this as P.F name when I say it out loud. But the arrow says, first resolve this guy to its value. All right, so now I'm changing F name to Bob, displaying it, which should be the same thing as before. Now, remember my display person struct, this guy takes an actual struct as a parameter, not the address of a struct. So I'll get an error right here because P, this variable, is of type person struct pointer. But I'm calling a function display person struct that takes in an actual struct, not a pointer to a struct, but the actual struct. So how do I get the actual struct that lives at P? How do I pass the correct thing into display person struct right here? How do I modify that line to pass the right thing? Because right now it's going to yell at me and it's going to say display person struct expects a struct as a parameter given a memory address. So what can I do to this line right here? Really, what can I do to this right here to make it resolve to the value that lives at that memory address, which is a struct, as opposed to P equaling a memory address? Put an asterisk before it. Star P. Star we read as the value at this address. The value at P is a person struct. How do we know? Well, because person struct, because P here was a person struct pointer, which means it's a variable built to hold an address which points to a person struct. And if I want to get that actual person struct, I have to resolve that memory address to its value. And I do that by saying star P in this case, the value at. Okay. So these two functions here look pretty identical, with a little bit of syntax changes, right? But the difference is, in this case, I'm passing a struct by value. In this case, I'm passing the struct by address. So changes I make to it will be permanent changes out in memory. So if I call change struct by address, this function right here is expecting a person struct pointer. So now I'm going to have an error on this line. It's going to say, wait a minute, change struct by address expects a person struct pointer. You've given it a person struct. How do I get the address of P1? What's the other syntax? We have a star and we have the ampersand. Give me the address where P1 lives, because that's what this guy expects. He expects me to give him an address. All right, so now I'm displaying my original P1. I'm changing it, passing it the address to the actual original P1. Not a copy of it, but the real deal. I'm saying this is where you can find it in memory. This guy then gets that address. He makes a change to the actual thing in memory. Then he calls display person struct, which takes a plain Jane struct. So this guy needs to resolve that place in memory to the value that lives there, which is a struct. It'll print out Bob Lippman 21. And then our final thing back here will be when we call it that second time, we'll see that the change was permanent this time, as opposed to temporary in our previous example. Oh, same issue I had before. I didn't prototype it. Change struct by address. Doesn't know about it because I didn't prototype it up here. So there's our Bob Lippman 21. It has been permanently changed because I passed it the address where it could find it in memory, rather than a copy of it where any changes it made here had no impact on this original place. All right, makes sense? All right, so I realize that this stuff feels a little intimidating, but as you go back through this lecture, I'm going to say there's going to be a risk of a quiz next class dealing with this stuff. Really slow it down and just focus on what those two separate syntaxes mean. An asterisk says the value at an address. So if we were to put this on a slide, pointer syntax. So we have two different places. So we're going to say uses and definitions. If we're looking at a use, star let's call this pointer variable, says to resolve the address stored inside of pointer variable to the actual value that it points to. Address of any kind of variable, could be a pointer variable, could be a normal variable. The address of a variable says to return the place in memory where the contents of variable actually lives. So we get direct access to memory. I can say int a is equal to 5, and I can say int pointer b is equal to the address of a. This will give me the place in memory where we have stored this number 5. Make sense? That's what that syntax says. So when I'm using variables that are pointer types or address types, this is how you read those symbols. When we are defining, so type pointer variable equals whatever, says to store the address of ... in the variable, let's just say in variable, since variable was defined to hold an address. So when I say type star, I'm saying this guy, this variable right here, is built to hold us something. It's a variable, right? I can create an int variable like I did up here. So then the kind of value I put in an int variable is a 5. I can also create an int star variable. This is a container just like any other variable container, but its ability is to hold one of these guys. Int star says the address of an integer, not an integer directly, but the address where one lives. Okay. All right, and then we wouldn't actually create a variable with the ampersand. So we're going to say ampersand does not apply to defining variables. It's just not part of what we would do. So we would only see the ampersand on the right-hand side of the assignment operator, taking something that was passed by value and extracting its address. All right, make some sense? Sounds like a lot, but really focus on our code example from class today, along with this slide. So focus on that for next class. There's I would call it a very high risk of a quiz on Friday covering this exact material. If you get this under your belt right now, the whole rest of the semester is going to feel a lot more comfortable, because I know it really feels like it's a lot of verbose language when we're talking about addresses and pointer this and address of this, and it's actually not that bad if you just get it straight in your head now. Okay? Questions, comments, concerns, bribes? I'll bring the tip jar next time. All right, I'll see everybody on Friday. And if I think about it, when I'm sitting in my office later, I'll throw together an old school string example where I actually use string cat, just so you have a real code example of it. You'll see examples this semester, but we allocate memory and stuff. This has to do with whether we owned the memory space of the string or not. That's why I couldn't change it. It's, unimportant for us, but promise it does work.